Hello, this screencast is to help you understand equilibriums. An equilibrium is a balance point in a reversible reaction. I'm going to use this example of a reversible reaction, which is the reaction between blue copper sulfate and white copper sulfate. Now, in chemical terms, the blue copper sulfate is a hydrated form, has 5 water molecules as part of the copper sulfate complex, and the white form is just anhydrous, that means without water, copper sulfate, and the water has been removed. So you can see the reversible reaction written here, and I've done a little visual to show you that the hydrated copper sulfate is blue and the copper sulfate without the water added to it is white. So there's our reaction. So how can we discuss this one? So this is a video of some Year 11 students heating some copper sulfate pentahydrate, and as you can see, as it is heated, it turns from blue to white. Now, towards the top of the boiling tube, you can start seeing condensation. There's the water that was released as a gas condensing further up the tube. How can we discuss this one? Well, first of all, you might get a question that says, write down the two reactions in a word equation. So I've done it as a symbol equation and a word equation. So the two reactions are copper sulfate pentahydrate becomes, with an arrow, anhydrous copper sulfate plus water. And the second reaction is just the reverse. Anhydrous copper sulfate plus water becomes copper sulfate pentahydrate. So don't get caught out by a simple question like that. It just wants you to show you understand the reaction will go in both directions. Now let's consider a visual for the actual particles. We've got a water molecule here, and we've got anhydrous copper sulfate as a white ball. And the water molecule collides with the white ball and forms hydrated copper sulfate, which is a blue ball. Okay, so if we have a closed system with copper sulfate pentahydrate only, we would say that the reaction is at 100% product. Okay, 100% copper sulfate pentahydrate. The other extreme is to have 100% copper sulfate anhydrous and water. Okay, now I'm using one molecule diagram of water to represent the 5 water molecules because it's going to be too complicated for me. So this is the other extreme. This is 100% product in the forward reaction. So let's consider a point at which the equilibrium is established. In this example, the equilibrium is established at 50-50. Okay, half of the copper sulfate molecules are hydrated and half are not. The question is, how can we affect this equilibrium? So if we increase the pressure, how will that affect the equilibrium? Right, the water is given off as a gas, shown here in the diagrams, the water molecules floating around. So the water is given off as a gas. So if we increase the pressure, the forward reaction to make a gas is going to be less easy to do than the reverse reaction, which is to take a gas away. If there's pressure restricting the amount of gas, then the reverse reaction is favoured, and the equilibrium will therefore shift to the left. Now, here's an alternative situation. We return to our 50-50 equilibrium. Now, in this question, I'm going to explain to you that the forward reaction is endothermic. So the forward reaction takes heat from the environment and incorporates it into the molecules. The reverse reaction increases the temperature. It's exothermic. So if we increase the temperature of the system, then the reverse reaction that gives out heat is less easy to do. The reaction that takes in heat is more easy to do because there is more heat available. So if we increase the temperature, that will increase or shift the equilibrium to the right to encourage the production of anhydrous copper sulfate and water. Okay, so an endothermic, where heat is taken in, is favoured by a high starting temperature. Should make sense. So the equilibrium shifts to reduce the effect of the change. Now we have at the moment talked about equilibriums being in a closed system. And normally that's what you would say. In a closed system you find a balance point. But we're just going to briefly mention what would happen if you added or removed materials. So here's an equilibrium that is stable in a system. So we've got around about 60 or 70% copper sulfate 5H2O and about 30% of the pentahydrate. Okay, so there's more anhydrous white particles than blue. But it's a stable equilibrium, so the forward reaction producing more little blue balls is balanced by the reverse reaction producing more little white balls. Now what we're going to do is we're going to add copper sulfate pentahydrate. Now the equilibrium was happy at 70% towards the right, so it will go back to that point. So we've added more pentahydrate, but if we leave that, the equilibrium will re-establish itself, so more water will be released and you will get back where you were, about 70% white. Okay, the equilibrium will re-establish itself. If you add more of the material on the left hand side of the equation, then that will be converted, so the original equilibrium point, as close as possible, would be restored. Consider this situation. Here's a 50-50 mix of blue and white, and what we're going to do is we're going to take away water. Now by doing that, we've disturbed the equilibrium. The equilibrium will try as best it can to return to 50-50. So more copper sulfate pentahydrate will be converted to anhydrous copper sulfate to try and get back to where the equilibrium was, roughly about 50-50. Okay, but 50-50 in terms of the amount of water that's available. Okay, now clearly it's not a balance, because in trying to get the water back to equilibrium, the anhydrous copper sulfate is favoured. So that's why we usually talk about a closed system. But if you remove something from an equilibrium, the equilibrium will shift to replace the loss. If you add something, the equilibrium will shift to accommodate the new stuff and try and dissipate it or get rid of it. Okay, so you now need to answer these questions. I'm going to pause or you should pause the video and try and answer these questions one at a time. First question: what is the effect on the equilibrium shown of increasing temperature? Have a look at it, think about it. Exothermic reaction is the forward reaction, endothermic is reverse. Pause the video, try and answer the question, come back. The answer to that question is that the higher temperature shifts equilibrium to the left, so you will make less ammonia. The exothermic reaction is not as easy to do, the endothermic reaction is easier to do. Reaction shifts to the left. Second question: what is the effect on the equilibrium of increasing the pressure? Pause, think, and answer. The answer to the second question is that higher pressure shifts equilibrium to the right to produce more ammonia. That's because the forward reaction produces less gas, the reverse reaction produces more gas. Under a high pressure situation, producing less gas is favoured. Here's a different equilibrium. No names here, just A makes B and C. A is a solid, B is a solid, and C is a gas. Endothermic reaction going forward, exothermic reaction going back. First question: think, pause, and answer. What is the effect on the equilibrium of increasing the temperature? A higher temperature shifts the equilibrium to the right on this case, and you get more BNC because the exothermic reaction is not easy to do. The endothermic reaction is easier to do if there's more temperature to start with. Next question. Pause and think. What is the effect on the equilibrium of reducing pressure? Less pressure shifts the equilibrium to the right. Less pressure favours production of a gas. If you're reducing the pressure, production of a gas is easier, so that will shift the equilibrium towards the right-hand side. You'll get more B and C. Final question. What is the effect on the equilibrium of removing some A? Pause, think and answer. Okay, as explained, removing any material from a balanced equilibrium state means the equilibrium will shift to try and negate what has happened. So if you remove A, the equilibrium will shift to the left to produce more A until the equilibrium system is about at roughly the same balance point again. If you're getting that now, congratulations, you have earned yourself an equilibrium badge, which is quite a difficult chemical skill to master. So congratulations on that. Have a look at another video and